So how can we use calculus to find the volume of a sphere, the problem we ended the last video on? You probably know a formula for the volume of a sphere, or could at least look one up, but did you ever actually derive it in your previous classes? Probably not. So let's do that here. How can we imagine using a big idea of Calc 2 and Calc 1 to solve this problem? This is a continuous problem, right? A sphere is a continuous sort of thing, but we'll imagine slicing it up into thin, easy to handle segments, right? So imagine slicing it into disks and adding up their volumes. So we could say the sum of all those disk volumes, or we could say the sum of the area of the base of the disk times the thickness of the disk, which in the other video we called height, but right now we're going to be, instead of thinking about it this way, we're actually going to be thinking about it this way temporarily, and so then we'd call each of those what used to be heights, we'd think of them as maybe a thickness. So that would be the sum of pi times whatever radius we're handling right now squared, like the ith radius, times the thickness of the ith disk. So let's try drawing it before we do much more from there. So we could say, let's draw a semicircle, and let's use a radius of big R. So it goes from minus big R to plus big R. And what's the formula for the boundary of a semicircle, or of the unit circle? It's basically x squared plus y squared equals big R squared. So now we're imagining rotating this around the x-axis. So I'm going to draw a rotation symbol like that, and hopefully we'll get the shape. So what we're kind of thinking of here is taking a planar area, the world's best cutout similar to a sphere, and rotating it around like that. And if you imagine doing that fast enough, you're going to sweep out a sphere, right? So that's what we're doing, and we're kind of imagining slicing this into a thin disk and then rotating that disk around to be like that. So you can see we're trying to draw in 3 dimensions. You're probably having more luck with it than I am, but it's good to practice whatever your state of skill is. So this is called a differential element. That is, its thickness is a differential, like maybe dx, and in this case it's a disk. Or you could think a very flat cylinder. So we're imagining taking a bunch of really thin slices and adding them up. Here they weren't so thin, here they were much thinner, right? Another way to think about this is that I'm putting little segments like this. This is an old CD that I chopped up, centered around the x-axis, and some of them are bigger and some of them are smaller. I actually have a bigger one here, and then we're adding up all those disk volumes. So another thing I want to point out, we're rotating around the x-axis. What's another way of describing the x-axis? It's the line y equals 0. Which is a little confusing, right? It's the x-axis, so you would think it's the line x equals something, but it's the horizontal line y equals 0, and that'll help us thinking about the radius later. So here's one disk, and I want to imagine another disk next to that, and another disk next to that, and another disk next to that. So I'm going to say for each position, x, find the radius and the volume of the disk. At x, and then add them all up. So let's say we have some generic curve. It doesn't even have to be this, this curve here. So something clearly not a sphere. And we'll call this f of x. And we've got some disk like that. What's the radius of that disk? That's just f of x, right? So we're doing area of the base, which is pi times r squared times the thickness. We could call this delta x, but we're thinking it's so small, we've like let delta x go to basically 0, and when we think of that, we think about calling it dx. And this r is at the current x value. What's the height, what's that value right there? At any particular x value, that's f of x. So overall, and then, so overall I've got pi times f of x. We're going to square f of x because it's a radius and we're squaring it, and then multiplying by the thickness. And you might be thinking, with the dx, what do I expect out front? And we said add them all up. That sounds like doing an integral. And generically, we just go from a to b. Here, for the sphere, we'd go from negative r to positive r. But this is our overall first formula for volume of rotation rotating around the x-axis, or the line y equals 0, using disks. So what would that be for a sphere? Well, we'd need to come up with what f of x is for this semicircle, which is x squared plus y squared equals r squared. So we'd say x squared plus y squared equals r squared. Solve that for y, which you could call f of x, and that'd be square root of r squared minus x squared. And notice you can't just cancel the squares with the square roots. Everyone wants to, but it doesn't actually work. So that's my function, and I'm integrating from negative r to positive r in that figure. So I'm going negative r to positive r, pi times my radius function, which is square root r squared minus x squared squared dx. So finally we got the integral set up, and now how would you solve this integral? Well, I said you can't cancel this square rooting with this square or that square because of the addition or subtraction in there, but here we are literally taking a square root and then squaring it. So you can actually cancel negative r to positive r, pi times r squared minus x squared dx. And is that hard to integrate? That's just a polynomial. So you should go practice it, and eventually you should get 4/3 pi r cubed. Can you see where you're going to get an r cubed Well, this x squared, when you integrate it, will become x cubed, and you'll get a 1/3, which might explain why that's there. The pi is still going to be there. Where's the 4 going to come from? Well, you're going to have this r squared, and you're going to be plugging in r's for x and stuff. So it takes a little bit of simplifying, but eventually you get to the classic formula for volume of a sphere.